Welcome to the Control Engineering webcast, How to Tune Servo Systems, Sensor Resolution and Sample Time, Part 3, sponsored by Aerotech. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slide or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of the webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speaker in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You can receive an email within a week with the link to the on-demand event. So we'll send that out about a week later. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents also will be available with the on-demand version of this webcast. Now we will hear from the sponsor of today's webcast, Aerotech. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation. I'm happy to introduce today's distinguished speaker. Dr. Profeta has more than 30 years of experience in technology-driven companies. He is director of the Control System Group at Aerotech with P&L responsibility for controls, drives, and motors. In this role, he works with companies to design and select control system architectures that result in increased machine performance while minimizing component cost. He has earned a BS, an MS, PhD, and Executive MBA. He has been awarded with 5 patents and published 43 papers. Dr. Profeta is also an adjunct professor in the Electrical and Computer Engineering Department at the University of Pittsburgh, where he teaches software engineering. Joseph will join us right after the following video.
Try to punch it. Okay, thank you, Mark, for that introduction. And I'm sure if you've been to the first 2 webinars, thank you for attending those, and thanks for coming to the third. Hopefully, the experience that you just saw there hasn't been as often since you have been attending the webinars. And today what we want to do is talk a little bit about digital controllers And what they bring in is we need to have a sample rate and a resolution that we pick. In the previous webinars, we just talked about the systems as if they were purely continuous and ignored the fact that it's really a digital controller. So the specific architecture that you have to deal with in general is you have a plant, and we call that GP of S, and we have some feedback transfer function we call H of S. But then that feedback transfer output or signal has to be sampled by the computer at a specific time. We like that time to be uniform if you can. Any jitter in that will cause some sort of small errors in the performance of the system. We compute a control law in G of Z, and then we have to output the signal, and we output it through a zero-order hold signal to get from the discrete domain to a continuous control signal that we apply to the plant. And so that's the general architecture that's used. Typically sampling that occurs with an analog to digital converter. And the question is, well, how many bits should I use? Typical converters are anywhere from 8 to 20 bits. Very common to use a 16-bit converter with an input voltage of, say, plus and minus 10 volts DC. And so we have a 20-volt range. We have 2 to the 16th counts. And so one A to D count is the same as 305 microvolts. And then we have to look at our sensor and say, okay, what's the scaling of our sensor? And we get then one A to D count is, let's say, so many degrees of motion. And so that's going to be our resolution of the system. And we want to look at how does that resolution affect the performance of the system. And then sampling also causes quantization to occur, right? We can only have a certain amount of distance in the time that we get information from the system and then provide a control output. Typically, and I'll talk about the examples here with servo motors, since that's most of my experience. So we have an encoder on the back of a servo motor or in the system, and that encoder produces a number of counts, and those counts are the resolution that we're going to deal with. A typical 1,000 line TTL encoder, after quadrature, will have 4,000 counts per resolution, and so one count is 0.09 degrees when we look at our scale factor. Why is sampling bad? Well, it causes a phase delay. It's a time delay of information. On the right top, I have a signal, and I sample that signal at 1 second intervals. Picture this, just you're driving on the street, and there's a stoplight in front of you that's red. There's a bunch of cars here, and you have this new special windshield that is black all the time, except for once a second, it gives you a flash of what you see in front of you, right? And so you get that quick sample of where you're at, and then you have to make some decisions in between there. Now imagine that, okay, the windshield, instead of flashing at 1 second, starts flashing at 5 seconds. That really would start feeling uncomfortable trying to stop on time. But now imagine it flashes at a kilohertz. That probably almost feels like real time to you, and almost wouldn't be bothered by that. And so that's really the question that we have here is how fast do we sample so that the control system adequately senses this continuous process so that it can control it. And so on the bottom signal on the right, you see, okay, now I sample the signal at 0.33 milliseconds each, and I feel like that representation of that continuous signal is much more faithful to what really is going on than the top one. And so we want to try to decide that. Another problem that we have with discretization or sampling is we can't really know what frequency we were looking at necessarily because of the Nyquist theory, right? It says we need to be sampling at least twice as fast as the signal. I show two signals here, two sinusoids, one at a frequency of 7/8 hertz and one at a frequency of 1/8 hertz. And if I sample that at 1 second intervals, from the controller perspective, I get exactly the same values, and I can't distinguish between those two frequencies. And so in the controller, most have some sort of anti-aliasing filters so that you know the signal you're seeing is really truly the frequency that's being registered in the continuous system. And often oversampling is used, where you just sample multiple times, you take some averages and help smooth out some of that noise as well. So those two types of filters usually should be present in your sample data system. Just a quick reminder of encoders, if you haven't used them very much. We basically have a disk. Around the disk, we have a number of slits, and we have some light with some LEDs that will shine through that. We have a fixed panel with two slits in it. We call those channel A and channel B, sometimes phase A, phase B. And then we have some detectors on the other side of that. And so as we rotate the disk, we have the light come through, and when it goes through both slits, you receive that. And so you basically see a number of counts that occur. We have two channels, and the channels are spaced 90 degrees apart. And so we get two signals that are square waves, 90 degrees apart, which gives us the ability to count 4 transitions, the up transition and the down transition of both of those signals. And so that's why I mentioned before, with a 1,000-line encoder, we get 4,000 counts per resolution, per revolution. Absolute encoders are becoming more common in systems. Really no difference from the perspective that we want to look at, which is, well, how many counts do we get per revolution? It's just that with the absolute, you know exactly where you're at when you start up. With the incremental, there's a C channel that you can kind of see on the inside of the disk at the top there. And when we pass through that C channel, we get a count, and then we know exactly where we're at. And we would often, on startup, have a home routine that would rotate the encoder around or the motor around. We see the C channel, we stop, and we go, okay, let me call that some prescribed, by definition, position, which is usually home or 0. There are amplified sign encoders, and these are encoders that in between the transitions of the counts, they really give you a sinusoidal 1 volt peak-to-peak analog voltage. And so what we can do then is take these two, and remember the A and the B are out of phase by 90 degrees, so one is a sine of theta and the other is a cosine of theta. And with a little bit of trigonometry, right, we take the inverse tangent of sine over cosine, and that gives us the angle. So what we can do then is sample that analog signal, and on the left bottom here, you see me sampling 8 times during that one period of a sinusoid. And so we would call that usually a multiplication factor of 8. I take 8 samples during one period of the sine wave. And if I was going to try to take faster samples, then I would want to have a higher multiplication factor. And so on the right, you see that I sample twice as fast, so I take 16 samples over that, and now I get twice the resolution by sampling faster. So this instrumentation to do this inverse tangent and do the sampling is often included in the encoder setup from most manufacturers, but also there are many drive manufacturers that also put their instrumentation in there. The benefit is if you're doing the multiplication in the drive, then you usually can count faster, which means you can reach higher speeds. And so that's one benefit to that. AS encoders, they're analog signals, and so you have different run lengths of wire and different instrumentation that is being used. And so there's some amount of gain difference and offset in each of the A and the B channels, the sine and cosine channel. And so in order to use that encoder properly, you'll need to adjust those values to be such that the sine and the cosine channel, remember sine squared plus cosine squared equals 1. And so what we can do is test the two signals and make sure that they are compatible. And we do that by painting a Lissajous pattern, which is a unit circle, and you can see that on the right in red, and then comparing my sine squared plus cosine squared to that Lissajous pattern and see how close I am. And then adjust the gain and the phase and the relative phase and the offsets so that I lay right on top of that circle. And so that's something that must be done. Remember, if you can't count, if you can't sense your system, then really you can't do anything. So I always start there. Start with the encoder, make sure it's tuned, make sure you're counting correctly, make sure it's the right number of counts per revolution before you start changing any gains or anything else, because if you can't count, you can't move. So we'll show you a small video of doing some encoder tuning.
So I have a servo motor set up with a amplified sine encoder. That means I get back a sine and a cosine channel, and each channel has a gain and an offset, and then there's a relative phase between the two signals. And so if you can't count properly, if you don't have good feedback, you really can do nothing. So the first place to start is with tuning the feedback and make sure that it's correct. I have my motor enabled and I can have it tune automatically. The red circle that you see is the sine squared plus cosine squared, which is called a Lissajous pattern. And basically there's a small search that's done through the gains and offsets to find values that have some least square fit to the Lissajous pattern. And when you get close enough, you say, okay, that looks good, and you stop it, and then you can save the gains off. If you don't have your motor tuned well enough to actually run it, what you can do is just disable it, do a data collection, and move the motor, which is what I'm doing now by hand, and you can see what the Lissajous pattern looks like. When you look at the Lissajous pattern, you can also tell something about it. If the gain is not near the circle and not equal to 1, as long as it's greater than a half, it's usually enough signal. But you can also see if maybe the channels are lopsided. So for instance, if the gain in the sine channel was substantially less, you'd get an oval, something like this. If your offset was off, you could see that you would be shifted from the axis by some amount. And then if your phasing of the system was not right, you would see some rotation of that ellipse about the axis.
So if you have some gray hair like myself, you probably worked with an analog control system, and you remember you had to get the oscilloscope out and try to get all the tuning done like that. So I enjoy the digital controllers much more because it's very easy to do that tuning. So let's talk about finite resolution. Why is it bad? Well, basically, as we said, like in the driving example, right? The control system doesn't get any information in between the samples, and when you have finite resolution, you also only have the same information in between the movement of the system. And so that quantization can sometimes cause a limit cycle where when you're trying to settle, you're flipping between one count and another count, and that's sometimes undesirable if that count is large enough. The other problem is the round-off error will introduce a white noise with an average power of Q squared over 12. So the average power of the noise you're inserting into the system is directly proportional to that level of quantization. So smaller is better, less noise. The final reason is while the system might be able to meet the performance specifications in, say, terms of settle time and steady state error, lower resolution will cause some amount of audible noise. And many of us just sitting there listening to the machine and hearing that noise, we don't like that. And so we want to try to eliminate that. So higher resolution will help eliminate audible noise. If you're working with applications that are really noise sensitive and you're trying to, say, measure the shake, rattle, and roll of a device, then higher resolution also may be beneficial to eliminate noise from the system. And then finally, while resolution can affect accuracy, you have to make sure that you have enough resolution to meet the accuracy that you're trying to have. And a usual rule of thumb is, well, you better have at least 10 times the resolution as the accuracy that you're trying to achieve. But so it's inconvenient to sometimes work in counts. You might have a very high resolution encoder and you're trying to make a move and say, okay, this is 103 million counts. User units are usually much easier to work in. Most controllers will give you the ability to work in user units. And so we'll define, let's say with my rotary motor, I'm going to work in degrees, and then I'll have a number of counts per degree that we can work in. And I'll call that K-res, my number of counts per user unit. And then the last thing, as I mentioned before, you need to make sure that your controller can count fast enough for the resolution you're using for the speed that you're going. I don't find that as a problem as often anymore, but it's still something to be thought about as you're selecting the components for your system. So the zero order hold, as I said, it's a digital to analog converter. And then basically what we do, and you see a sinusoid here, if this was my control signal, U of t that I was trying to produce, but I only get to put out a value and hold it, this is, you know, a series of steps. And you can see here in the blue line, if I'm sampling and outputting at 1 kilohertz, I'm going to have a series of steps. Whereas if I was sampling and putting out values at 6 kilohertz, I would have a much closer representation of that sinusoid. Well, it's a linear system, so just picture that every millisecond I'm putting a small step in. I'm going to have a step response to that, and I have some oscillation, I have a little bit of overshoot. And so this introduces some movement in the system that might be undesired or not as desirable. So minimizing that sample time can help us minimize the amount of time the zero order hold puts the step response in and will give us a better response to the system. So in the previous two webinars, we had talked about the S domain, the Laplace domain, because we're just thinking of the systems as continuous. But now that we've introduced this idea of a digital controller, we need to have a different domain, frequency domain tool to work with, and we call that the Z domain. And it's just a discrete time implementation in the computer, and we think of, instead of a linear set of differential equations, we think of a linear set of difference equations. And they're very similar in nature. And if we look at what that discrete time equation looks like, we see here in the middle of the screen an equation U of k is equal to A1 times U of k minus 1. Well, we can think of this as a just set of multiplies and adds. That's all it simply is, where I take a set of coefficients that are constant, a's and b sub i's, and I multiply those onto the current value of the error and the previous values of the error, plus the previous values of the actuation signal, and I add all those up and I get my new actuation signal. And so the ideal is that I sample the plant with my A to D, I execute this equation as quickly as possible, and I put out a value for U of k, and then I do whatever cleanup I need to do, right, shifting the old values back so that the next sample period I'm ready to recompute this equation. There's a clock in this system, and you need the clock to synchronize all the parts so that we're sampling and putting out a value at the same time. We talked about how to use block diagrams. So just a quick reminder, right? So if I'm looking at the control loop here with the feed forward in red GFF of S, the output of that block, YFF of S, is just equal to the transfer function in the block, GFF, times the input of that block, which here is YD of S. And so that's the simple rule that we need to follow. And the problem is we can't really do this in the system that I've shown you. I have on the right an analog continuous time domain plant represented in the Laplace domain, and on the left box, the computer, I have a digital controller. So I can't just multiply GC of Z in the controller times GP of S and make any sense of that. So I need to create some sort of reasonable model of the system, and I'll have to do that all in the digital domain. And so I'll talk about the Z domain as the discrete frequency domain. I don't mean that to be a set of discrete frequencies. I mean that to be a discrete time signal that we take the Z transform of. And so basically I have a continuous time signal, and I can transform that into the Laplace domain. If I sample that signal, I get a set of discrete points, and then I can apply a Z transform, and I'll get a transfer function in the Z domain. And so the simple thing that we would do is take the plant, and we would transform that, and we would completely have a Z transform model of the system, and we could use that to do analysis. When I do that, I'll end up with a transfer function that looks like this. U of Z over E of Z is equal to a set of coefficients B sub I and A sub I times Z minus 1 or Z minus 2 or Z to the minus M in the numerator, and 1 minus A, 1 Z minus 1. And Z to the minus 1 or 1 over Z is just a sample time delay. So you can see there's a one-to-one correspondence between this transfer function and the actual equation that gets implemented in the controller. And so that makes it very useful and very easy to translate from one domain to the other. Now, I'm not going to go through the theory of the Z transform and how to get these equations, but from a practical perspective, it's very easy to think about a couple simple approximations from the Laplace domain to the Z domain, or from S to Z. And for that, I just need to take you back to your very first calculus class you ever took. Remember, in the Laplace domain, 1 over S is integration. And so let's just think about the theory of integration and how we find that. Well, integration is just the area under a curve. And there was 3 different methods that we studied to do that. One was a forward method, one was backwards, one was trapezoidal. And so if I look at this curve and my sample time is T, shown here in the first block in blue, I consider that my sample time. Then if I'm going to do a forward integration, the forward rule is that S is just equal to, or approximately equal to, Z minus 1 over T, T being the sample time. And the backwards rule is S equals Z minus 1 over TZ, and the trapezoidal rule is S is approximately equal to 2 over T times Z minus 1 over Z plus 1. The forward rule we can't really implement because it demands that we know the point in the future, which we don't know. The most common thing that you see used is the backwards rule, which is the center one. However, the trapezoidal rule is really the best approximation. And sometimes we hear that called the bilateral transformation, or sometimes Tussen's formula. There's various names for that. So the 2 most common things that you'll see are backwards and trapezoidal. But the important thing to take away from this is that the transfer function is a function of the sample time. And so when we change the gains, or let's say it this way, when we change the sample time of the system, we necessarily must change the gains of the PID system, or the controlled law, so that I can maintain a constant loop gain. Otherwise, I may destabilize the system because I have gains that are way too large. And so this is why with a discrete controller, I do need to change the values of the constants, Kp, Ki, Kd, when I change the sample time. Now, how do I know how to change them? Well, let's take a look at the full system here. So I have a plant on the right represented by an inertia that I'm going to move plus a resonance. That's the 1 over J, 1 over S, 1 over S, and the S squared plus 2 xi omega 1s, so plus omega 1 squared divided by S squared plus 2 xi omega 2s plus omega 2 squared. That's a flexible body. So I sample that system. Let's say I'm going to rotate this motor. I'm going to sample that system, and then you can see in the feedback that I differentiate that Z minus 1 over TZ, and I use that as my estimate of velocity, and I take that position feedback and I compare that to YD of Z, which is the command, generate an error signal, and then I have an inner loop, which is a velocity loop, and I have an outer loop, which is a position loop. And I have three gains, the K pause, the KP, and the KI, that I need to adjust appropriately to stabilize the loop. If I write the control law using that simple block diagram rule that I showed you for U of Z, which is the output of the zero order hold, then I would have this equation here. And what I want us to look at are the terms in red. So KP and K pause, you can see, are divided and multiplied by the sample time t. And so if we're going to determine how the gains change, let's just take them from right to left. So the integral gain, K sub I, not multiplied by the sample time, so it's not affected. So when I change, let's say I increase the sample time, then my Ki that I had will still be my new Ki. I don't change it. Let's look at the next term. So K pause times T, it's multiplied by T. So if I increase the T, then I'm going to have to decrease the K pause proportionally. And so the equation is just the ratio of the old over the new sample time times the old gain is equal to the new gain. And then likewise, I can see that Kp divided by T, well, if I increase the sample time T, then I'm going to have to increase the Kp proportionally. And so the equation here, just the ratio of the new to the old sample time is equal to the new Kp. And then I have this fourth term. It's not multiplied by T, but looking at Kp and K pause, well, I know we're going to change those, but we're going to change them inversely proportional. So Kp will change up, K pause will change down. The ratio is the same of the change, and so the product of those doesn't change. So that matches our control law as it should. So I didn't write the equation for the feed forward, but you can write that same equation in the same way, including that, and you'll find that the feed forward gain doesn't change when I change the sample time selection. It's just the Kp and the K pause. Now, that's not true for every control architecture. It's true for this specific control architecture. You have to look at the control architecture, write the equation for the control law, and then look at where does the sample time multiply or divide the various gains and decide how to change them as appropriately. So if I had a textbook PID, the answer would be a little different. Now let's consider the resolution change. If I look at the resolution change of the system, I'll include this block KRes, the red one, which is my counts per degree. And there's also some sensor noise that gets added in, N of S, right? I talked about Q squared over 12 as the amount of power in that quantization problem. And then I sample that value and bring it back in. So if I write the control law in a similar way, and again, I left out the feed forward term, I get this equation. And so now I had to rearrange the terms a little bit to make it a little bit more clear when you look at this, but I basically have the resolution, Kres multiplied onto Ki, and I have Kres multiplied onto Kp. That occurs in two different places, but exactly the same. And so what I see is, as I, let's say, increase the resolution, I'm going to need to decrease Ki and Kp. But I don't need to change K pause at all. It's not affected. And so I can write the two formulas here for the ratio of the old and new resolution. For those, K pause doesn't change. And again, if I go through the same exercise, I can show that the feed forward gain needs to change with the ratio of the old to the new resolution. Okay, here's a quick video on changing resolutions.
Now that we have the equations to change the parameters based on changing the resolution, I have opened the configuration manager. I have the encoder multiplier set to 65536, and I'd like to lower the resolution, so I'm going to change the multiplier to 1000. And Some controllers will build those formulas in for you, so when you change the resolution, it automatically will change the gains that are necessary. So I can accept those, and then I'll need to go ahead and send those to the controller and commit them into memory. Some parameters, such as resolution and sample time, are fundamental to the operation of the controller, and so it's necessary to reset the controller for some of those parameters. If you don't reset, you'll have a resolution which is inconsistent with the parameters that you've changed, and the system won't really work as you.
So as you see, these formulas are often built into the controller, so you don't need to worry about them too much. They're not always built in, but you know how to figure them out now. So let's look at some real data. So I have a servo motor set up with an amplified sine encoder. I have a small disc on it to give it some inertia. So it has a little bit of resonance in it, but not a lot. And what I've done is done a series of motions and collected some frequency responses and some time domain responses by varying both the resolution and the sample time, and we can take a little bit of information from that data. So you see here a set of frequency responses that are taken over a variety of sample times or sample frequencies. The specific frequencies I did in this set of data are 1 kilohertz, 2 kilohertz, 4 kilohertz, 5, 10, and 20 kilohertz. So just trying to get a nice broad spectrum of what that looks like. So the first thing you notice is, well, the gain curve, which is the top curve, below the cutoff, which is that red line there below 70 hertz, they look almost identical. And that's to be expected, because when I change the gains proportional to the frequency response, I locate the zeros of the control algorithm, or the control law, exactly in the same space. So I really would expect to have a very similar response. So I'm trying to compare apples to apples and not, say, have a higher bandwidth for one frequency than the other. I wanted to try to compare exactly the same system, but the only thing that we change is the actual sample time or the sample frequency. And so if I look at this system, I do have a general trend down in that the higher the sample frequency, the lower the gain margin that I have, but not substantially. It's not a substantial difference. If I look at the phase margin, I do get a substantial difference in phase margin here, right? The general trend is up. I get more phase margin as I increase the sample rate. That's really the expected result. Let's take a little closer look at these curves. So you can see the gain all lays on top of each other up to about 150 hertz. But looking at 150 hertz, the bottom curve is the system with the sample rate of 1 kilohertz, and the top curve is the sample rate of 20 kilohertz. I have 23-degree more phase margin for the 20 kilohertz system than the 1 kilohertz system. And so while I proportionally change the gains to have exactly the same response, when I look at this, what it tells me is, oh, I could raise the gain of the 20 kilohertz system way more than I could raise the gain of the 1 kilohertz system. And if I raise the gain, I'm going to move the crossover frequency out, and I'm going to increase the bandwidth of the system. I'm going to have a better response. So as formulated here, I have an identical response, but what you can see from this is I have the ability to increase the bandwidth of the 20 kilohertz system beyond what I can with the 1 kilohertz system. And that produces better performance of the system. Let's just take a look at some of the time domain moves. So here's the simple move that I made, just the index move. I moved 90 degrees. The top line here is the position coming in. The second line, rather uninteresting, is the position feedback. It looks substantially close. The bottom line is the position error. So I can see a little bit more interesting data here by looking at the position error. And so I'll just focus on looking at that as we go forward. The two lines here measure what the settle time is. I picked an arbitrary settle distance of 0.1 degrees for this, and then all the comparisons I'll do are relative to that. And so I asked the question, how long does it take after the move velocity is 0, which is the end of the move, how long does it take to settle to less than 0.1 degrees? If I just plot the position feedback for all the different frequencies, they basically lay on top of each other. They're so close it's hard to really see at that level. But at the air level, looking at the position air for all those frequencies, again, really, they all lay on top of each other. So in the previous slide I mentioned, but in the 20 kilohertz system, I have the ability to raise the gain a lot more. And so that gray curve that you see there is the 20 kilohertz system optimized. I raised the gain, and I then reran the response, and you can see drastic difference in the position error, much lower, and my settle time is much faster, right? So for the same, for two different frequencies, 1 kilohertz and 20 kilohertz, I have more ability to increase the performance with a 20 kilohertz. Now, I did all of this at the highest resolution possible on the controller I was using, so 262,144,000 counts per revolution, so very high resolution system. I didn't want the resolution to get in the way of the results of looking at the sample time. So let's take a look at what happens when I change the resolution. So I picked a sample time of 10 kilohertz, and now I made a move of 90.15 degrees. And the reason I did that is, well, the first move I made with 1,000 counts was 90 degrees. Well, 90 degrees is a perfect 250 counts, and it zeroes right in. I'll talk about that a little bit later. So I picked 90.15 because I wanted to really see the effect of this resolution on the system. So the 1,000 counts and the 4,000 counts, you can definitely see the error in the discretization of the system. Somewhere around, it looks like 10,000 counts, you basically can't really see any difference between 10,000, 100,000, 1 million counts per revolution and above. So at this 10 kilohertz, basically 10,000 counts per revolution and above have very similar, if not identical, responses. And then I moved up to 100,000 counts, and I did this at 1 kilohertz, right? I did this at 1 kilohertz, repeated the experiment for all these different resolutions. And what you see is now at 100,000 counts and above, the response is about the same. So I lowered the sample time. I needed more resolution to get an equivalent step response performance. And so there's a little bit of trade-off. You can't just think about one versus the other. It's a little interesting to think about, well, if I have a lower sample time, I probably can do with less resolution, and vice versa. So I was tempted with these only 2 data points to say, well, as long as the product of the two are 100 million, then you're going to have good results. But that would be unfair to make that assessment on 2 data points. So let's look at the sample rate and how that affects the time domain performance. And again, all of those same responses I plotted here. So the settling time, as I increase the sample rate, it goes down. I get a faster settle time. And if I look at the steady state error, there's some small decrease, but if you look at these numbers here, they're pretty small. It's relatively flat, but still there is a general trend down. And then the overshoot actually does increase a little bit. And this is a critically damped system, so it's really the undershoot that we're looking at here in that sense. And the undershoot goes down a little bit. But again, if you look at those percentage values, they're all so close that really I'd want to count that as a straight line. So let's try to compare this idea of resolution versus the sample rate at the same time. So here's a plot where I have 1,000 counts per resolution, and the yellow is 10 kilohertz and the blue is 1 kilohertz. Oh, the yellow is a little bit maybe worse in some areas and better than others, but basically I would call this a rather unacceptable response. There's a lot of noise in the system, And if I look at the peak error, it's like almost 1 degree at the peak. If I now step up the resolution to 4,000 counts per revolution and compare 1 and 10 kilohertz, much better response from both, but still I can see some of the effects of the quantization and the sample time. And then if I move to 100 million counts per revolution and compare the 1 to 10 kilohertz, almost no difference, right? And I've minimized my peak error and the settle time of the system. My conclusions from this, well, higher resolution yields more improvement than the sample rate, right? As I increase my resolution, I get more effect on the system response than if I increase my sample rate. At some sample rate, the response is degraded enough that I find it unacceptable. So resolution also will affect your accuracy, right? You need to make sure that you have enough resolution for the accuracy you're trying to look at. And so here I did a 90-degree move, and you got to be careful not to be deceived, right? My position error plot shows 0 error, but I tried to move it 90.15 degrees, and so I show 0 error because I settled at 90 degrees, but I don't know that there's really some offset from what I truly wanted. So the real error here is 0.15 degrees, even though what I look at in the scope is 0 degrees of error. And so if I do a summary of the step responses I did, right, there's some slight increase in the overshoot with higher resolution. There is some settle time. It's basically the same over 10,000 counts per revolution. You can see it flattens after that. And then if I look at the steady state error, again, over 10,000 counts per revolution, I'm basically flat across all these different resolutions. And the results are independent of the sample time. There's no difference. The sample rate affects the phase more than the resolution. So let me take you back to that same set of frequency response curves. The top set of curves was at 10 kilohertz across all resolutions, and they form a very tight band. There's really no difference. And then if I look at 1 kilohertz across, and I just did the top and bottom resolution, again, the same, right? So there's really much more difference in your phase that is caused by a change in your frequency, your sample time, than by changing your resolution. And so that's going to give you that extra phase to be able to raise the bandwidth of the system. And so if I look at, in the frequency domain, my gain, my phase margin, my crossover, again, it's more affected by the sample rate than the resolution. I have basically a flat line when I compare across resolutions, but when I change the sample rate, I get a whole different line that I look at. And you can see that in these 3 curves here. So, is more always better? Well, consider a very high sample rate with a very low resolution on, say, a spindle. I'm going to get so few counts per sample rate that I've actually found lowering my sample rate gives me a better control in that system, right? So it's not always better, but almost always better, right? And you got to remember the system's non-linear. You might be able to optimize your system for one specific move, right? I didn't mention it, but there's a flattening of the gain curve in the frequency response, and that shows me there's friction in the system. And so that friction might actually work to your advantage at a lower resolution for some moves, but not for all moves. And so my overall conclusion is, well, for sample rate, yeah, faster is almost always better. For resolution, more is almost always better. From the data I collected, I saw nearly identical performance at 10 kilohertz and above and 10,000 counts and above. So thank you for attending the webinar. The first 2 webinars are out there for you to review if you'd like. They give you the basics of the frequency response and how to tune feed-forward gains. And today we focused on the sensor resolution and sample time. I'm planning on doing a fourth webinar, which would be on force control and how to set up the loops and how to set that system up. So hopefully you'll join us for that. Thank you.
Thank you, Joseph. We have some time for some questions. Next slide, please. The audience may type questions for the presenters in the Ask a Question box on the screen, and we'll get to as many questions as time allows. Questions that we do not get to today will be posted online at controleng.com with the archived version of this webcast. Remember to download a certificate of completion or a copy of the presentation. Use the Event Resources tab on the left side of your screen. And now on to the questions. So the first question, Joseph, you mentioned audible noise. What causes this, and why is this an issue?
So the audible noise that I was talking about can come from the encoder. Usually that occurs when you're using a TTL encoder that's very low resolution, 1,000 counts per user unit, in this case a degree, or maybe even 4,000. You'll just hear this broadband white noise kind of when you're running the system, and that can be eliminated by just moving to a much higher resolution encoder. So by using an AS encoder and a high multiplication factor, you'll eliminate that noise. And when you're maybe trying to test a system that you're listening for how loud that product is, in common use, that might be important to you. Or generally speaking, if you're deploying machines, your customer just may find that unappealing to hear this noise all the time, and it'll be a little unsettling. So you can eliminate that. The downside is, well, higher resolution encoder costs a little bit more money. So at the trade-off of a little more cost, you can have a little less noise.
Great, thanks. So why would you not always use the highest sample rate or the highest resolution?
So two reasons. So the first is, what I didn't talk about is in between that sample time, right, during that sample time, you have to compute the control law. You may have programs running that are doing other things on the machine that are time sensitive, and you might not be able to complete all that work in a smaller sample time. So by necessity, you may be forced to have a larger sample time to accommodate all of those calculations that need to take place. The second is that one example I gave you of the spindle control, a very high-speed spindle. Maybe you're better off with a lower sample rate so that you can get more counts if you don't have the option of changing the encoder resolution, right? So that might be a situation. And every once in a while in a system with high friction, I've noticed, okay, it is nonlinear, right? So in a linear system, if the world was completely linear, I'd say, well, yes, always use the highest one. But every once in a while, you'll find situations where that's not necessarily the case.
Great. Would the conclusions made be valid for linear amplifiers?
Yeah, I believe the conclusions are valid for linear amplifiers, and in fact, I think the linearity in the data would be even more increased or more pronounced. You saw some of the lower data points didn't exactly follow the trend line, but I think that would be more pronounced because you're using the transistor in its linear region and you have more control over the current that's being put out.
Great, thanks. The audience can continue to ask questions, and we'll get to as many as time allows. Questions that we don't get to will be posted online at controleng.com with the archived version of the webcast. So keep the questions coming. And you also can download your certificate of completion or a copy of the presentation by using the Event Resources tab on the left side of the screen. Here's another question. What if any, is the effect of bearing lubricant viscosity on the machine stability?
So the lubricant obviously will reduce your friction. Depends upon your environment, sometimes you're in a clean room and you have to use special lubricants for that, and you have to make sure you use the right ones. But generally, either outside or inside the clean room, you're going to be reducing your friction, which means that as you come to settle in, those small steps will have more responsiveness in the system. So at the lower resolution with the high friction, those small steps might not be quite noticed as much. And so that's really what the effect is. But if I can eliminate friction, I think that's always better. So I do recommend providing the right lubrication.
Great. What do I do when the gearbox backlash is inconsistent due to forces on load?
So if you have a gearbox in the system, and by inconsistent, I assume that you're saying, okay, if I go reverse and forward, reverse and forward, I don't exactly go back to the same place. So one way to handle that is with your control architecture, right? Include two encoders and be measuring on both sides of the gearbox so that you can really compensate for that nonlinearity in the gearbox. The other method is sometimes if you only can really have one encoder on the system, well, a lot of controllers have the ability for you to measure that and take your best guess of what it is, and then you arbitrarily add counts based on the direction that you're moving. But there will still be some small residual error that you can't account for in that situation. And I would suggest that the lower the resolution, the more effect that's going to have, because you're just kind of banging it with little step responses, and that will exaggerate those nonlinearities, I believe.
Great, thanks very much. What's the relative advantage or disadvantage of PID position loops versus cascaded position velocity loops?
So if you have the cascaded loops, two things come to mind quickly. The first is you can have a velocity loop and an hour position loop, and with that structure, you cannot pick gains that will give you complex zeros. And it's those complex zeros that can cause oscillation. So for instance, if you would put the complex zeros over top of the complex poles that are in the resonance, you would create a situation where you would have intersample ripple in the system and you couldn't do anything about it. But if you have a two-loop system, it forces you to put the zeros on the real axis, and you can't cause that situation to occur. And so that's very useful. The second thing is, if you're doing dual loop and you have two encoders, like I mentioned with the gearbox, well, now you can use a feed forward term, which I didn't talk about here, but the KV term that was in the slides, to match up the relative resolutions of the two encoders. You don't actually have to use the same resolution encoder on either end of the gearbox or for the two systems, for the position and velocity loop. And so those two things come to mind.
Okay, here's a long question. Help me out here. Increasing K-res seems to be the same as increasing the sensor's amplifier gain. It seems to me that boosting the sensor resolution may have a different effect, such as lowering the quantization noise. Can you please comment on that? Okay, so I'm going to interpret this a little bit. So by saying increasing the sensor amplifier gain, I'm going to say, okay, we're talking about an analog sensor that I have a gain I can increase in the analog domain, and then I sample that with, say, the K-res, okay, in which case I would say, yes, generally they have the same effect of how I need to change the gains in the system. However, changing K-res, I think it's correctly stated here, right? Depending on how I change K-res, I can lower the quantization noise, whereas if I just change the gain in the amplifier, that won't happen. On the other hand, there's other effects, right? So if I would raise the gain in the analog domain of the sensor, I might increase the shot noise of that instrument, and I don't know what that noise floor would be. So there'd be some trade-off to take there. Great. How does latency affect the response? Is this more significant than the sample rate?
So I'm not exactly sure what the person is asking by latency, because my first response is, well, latency is take a sample. Oh, I see the question. Okay, so by latency, I guess we're talking about like a time delay, right? A time lag, and that will increase and cause a phase delay. You could think of them as basically being the same thing. If you look at the phase is directly proportional to the amount of time that it's delayed, right? So the sample time is a delay of time, and you can calculate what the phase difference is there. So they would have similar effects, but not identical effects.
Great. One more question to wrap up. What is the most overlooked area regarding sensor resolution and sample time in tuning servo systems?
Can you repeat that one? Sorry, I didn't quite catch the whole thing.
Sure. What is the most overlooked area? So when considering sensor resolution and sample time in tuning servo systems, is there one area or several areas that are most overlooked when doing this exercise?
Yeah, so I think the most common conversation I have with customers is, you know, hey, let's increase the resolution of the encoder, and so the data I took was on a fairly benign system. There was no real resonance in this system. Okay, so if I increase the resolution and I increase the sample time, I'll be able to measure, quote, those higher frequencies better, and if I can measure them better, I can control them better. I can put in notch filters that are more high fidelity and really cancel out those resonances, right? Like, for instance, the one curve that at a kilohertz, I can't even see anything above 500 hertz, so I have no chance to put a notch filter at 1,000 hertz if I have a resonance there. So in real systems, complicated systems, machines, right, there are resonances all over the place. And so the higher sample time, higher resolution is going to give you more benefits there, which translates into better, you know, time domain performances that we're usually thinking about, which is overshoot and settle time and steady state error.
Thanks to the audience for the great questions. We'll try to get as many to the unanswered questions offline as we can. Thanks to our presenter, Joseph Perfetta, for sharing time and expertise with us. Who wouldn't want him as a calculus professor, huh? So I'd like to extend special thanks to our sponsor, Aerotech, for sponsoring today's event. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. On behalf of Control Engineering and Aerotech, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.